Lesson 7.2 is representing combined probabilities with diagrams. So we're going to be looking at representing sample spaces and specific events using different types of diagrams. The first one we're going to look at is Venn diagrams, which is something that you've probably used in your English and social science classes to compare and contrast things. So just a little brief overview. You have your rectangle on the outside. This represents everything in here, represents every single thing in your whole sample space, so all the possible outcomes. And then if you're looking at, like, let's say 2 different events here, you have event A and event B. Anything that's in the circle of A are outcomes that work for event A. Anything that's in the circle of B are outcomes that work for event B. And then anything that's in the overlap is something that works in both. If you look at something like this one here, you can see that all the events or all the outcomes in event C are also in event A. So that would be something like this. Versus this one, everything's equally sized. You have ones that overlap just between 2 and ones that overlap between all 3. So this first example, it says, in a class survey, Ricardo, Melina, Daniel, Maria, India, and James reported that they study environmental systems and societies. India, Pietro, Mathea, and Hanine said that they studied geography. Ricardo and James were the only ones who reported they studied Spanish, whereas Sophia and Yulia studied none of these subjects that were mentioned in the survey. So the first thing we want to do is represent this data in a Venn diagram. So this is how I created my Venn diagram. So I have 3 circles. I have the circle for environmental systems and societies, I have the circle for geography, and I have a circle for Spanish. And then I have my rectangle on the outside that represents the entire sample space. So then I went through and I figured out where people went and where people overlapped. So for example, India studies both environmental systems and societies and geography. So they're in the middle here. Pietro, Mathea, and Hanine only study geography, so they're outside the ESS circle but inside geography. Ricardo and James study both ESS and Spanish. And so I put a circle inside the ESS circle to represent Spanish because those are the only overlap there. So I put Ricardo and James inside this smaller Spanish circle. And then Melina, Daniel, and Maria are outside that circle but still in ESS because they are only taking ESS. And then Sophia and Yulia, they're outside all the circles but inside the rectangle because they're in the sample space. They're in the universal group, but they're not taking any of these classes. So then when you're looking at a sample space like this, if I want to look at, for example, for number 2, it says find the probabilities that a student chosen randomly from this class studies ESS. So everybody in this whole circle studies ESS. Melina, Daniel, Maria, Ricardo, James, and India all study ESS, even if they're in a shared one too. So go ahead and pause the video and find the probability that if I randomly chose a student, they would study ESS. So find the probability that someone studies ESS. So I counted up all the students who study ESS, and there's 6 of them. And then I counted up all the total students that were surveyed, and there were 11 total. So therefore, 6 out of 11 students study ESS, or 0.545. So go ahead and pause the video and try B through D. So B says that they study ESS but not Spanish. So that would be Melina, Daniel, Maria, and also India, because India also studies ESS but not Spanish. So there are 4 people total that study ESS but not Spanish out of the 11 total surveyed. So you'd end up with 0.364. For part B, it says studies all 3 subjects. There is no overlap between all 3 subjects, so there are 0 students who study all 3 subjects out of 11, so your probability is just 0. And then the last one says the probability of a student who studies exactly 2 subjects, so that would be Ricardo and James, who study both ESS and Spanish, and then also India, who studies ESS and geography, and so you end up with 3 students out of the 11 surveyed, or 0.273. For this next example, it says in a class of 26 students, it's found that 10 study geography, 16 study history, and 4 study neither geography nor history. And we want to draw a Venn diagram that represents this situation. This one's different than the previous example because we're not given names, so you're going to end up just putting the total number of people in each group instead of listing out all of the different events. So go ahead and pause the video and try making a Venn diagram that represents this situation. So for my Venn diagram, I have my rectangle that represents the entire sample space, and then I have my 2 circles, one for history and one for geography. So then outside of both of the circles are the 4 students who study neither history nor geography. And then for the history and the geography, I have 12 inside the just history circle and 6 inside just the geography circle and 4 in the overlap. So I'll talk about in a minute how we found those. But the entire group for history is 16 and the entire group for geography is 10. So then calculating the number of students who study both history and geography, if you add up the 10, 16, and 4 that they tell you, there's more than 26 students. So that's where your overlap comes into play. Whatever over that is how many are studying both. So the way I thought about it was that this 26 total students who were surveyed had to be the 10 who studied geography, the 16 who studied history, the 4 who studied neither, and then minus, I called it X. And X is going to be this overlap because when you add up the 16 history and the 10 geography, you double count the overlap. So I'm going to take away one of those overlaps, and that's going to be how many are in the overlap. So when I solve this, I end up with X to be 4. The total, if I added all 3 of these groups up, was 30. So that means I double counted 4 students. So there's 4 students in the overlap who study both history and geography. So then to find the 12 and the 16, I just took the 16 students who study history and I subtracted 4, which means 12 are studying only history. And then same thing with the 10, I took the 10 students who are studying geography, that's the whole group, and I subtracted off the 4 that are studying both, and so that's the 6 that are just studying geography. So now that we have these numbers, go ahead and find the probability that if I randomly select a student from this class, they study exactly one of these subjects. So 12 students study just history and 6 students study just geography. So those 18 students are the ones who study exactly one subject out of the 26 total students, so 0.692. Another diagram that we use a lot of are sample space diagrams. And there's a few ways we can do sample space diagrams. A common way is by doing a table. So we want to create a sample space diagram that represents the total thrown by rolling 2 standard 6-sided dice. So we're going to create a table that represents this situation. So along the top of my table here, I have our first possibility, which is die number 1. I could get anything from a 1 to a 6. And then along the vertical, I have die number 2. So that is going to be all the possible outcomes of my second option, also 1 through 6. So now go ahead and create a sample space diagram that represents the total if you throw the 2 die. So in this case, you're just adding the row and the column together, and so everything here in purple is our sample space diagram. So when you throw 2 dice, this would be all the possible outcomes of the total when you add the 2 dice up. So this is a sample space diagram just representing every single possible outcome in an organized table. So then for this example, they're saying that it's claimed that when you throw this pair of Cyckerman dice, the numbers obtained when they're added together have the same probability if you throw 2 normal 6-sided die, so the sample space that we had previously. So we have 2 die here that look like this, and so we want to create a new sample space diagram that represents throwing the total of these 2 Cyckerman diagrams. And then once you've done that, answer part B, use the sample space diagram we used on the previous slide for the 2 regular 6-sided dice, and then this one for the 2 Cyckerman die, and decide whether or not that the probabilities are the same. So here is the diagram space, or the sample space diagram. So along the top I have the die that's 1, 2, 2, 3, 3, 4, and then along the side I have the 1, 3, 4, 5, 6, and 8, and I found the totals here. So in order to verify the claim that the probabilities are the same, I'm actually going to find the probabilities of throwing each of these 2 through 12 for the 2 different sample space diagrams and figure out whether they're the same. So if you haven't already done so, go ahead and pause the video and do that. So I found the probability. In purple is the probability from the previous slide sample space, the 2 regular 6-sided die. So the probability of a 2 is a 1 out of 36, a 3 is a 2 out of 36, so on and so forth. 7 is the most common because if you add the top and bottom, they always add up to 7. And then in pink here is the Cyckerman dice, the sample space for that one. And so again, same thing I counted. So the probability of 2, there's only 1 out of 36 possibilities. Same thing with 12. For 3, there's 2 out of 36 possibilities. Same thing with 11, and so on and so forth. So all of the probabilities match from both the sample space diagrams. So therefore, yes, the claim is true. The probabilities are all the same whether you add up 2 regular 6-sided dice or these 2 Cyckerman dice. So for this last example here, we're going to use the sample space diagram from the previous example with the 2 Cyckerman dice. And if you throw 2 Cyckerman dice, you want to add up the total, you're going to find the probability of A, at most 4 shows up, B, a factor of 24 shows up, or C, at least 8. So try those 3. So for the first one, at most 4, which means it could be 2, 3, or 4. So I called this event A. So the probability of event A is the probability that you roll a 2, 3, or 4 combined. So a 2 was 1 out of 36, a 3 was 2 out of 36, and a 4 was a 3 out of 36. So there's 6 different ways you can add them up and get and get at most 4. So 6 out of 36, or 0.167. A factor of 24 for part B, that would be 2, 3, 4, 6, 8, or 12. There are 17 ways you can add them up and get a factor of 24 out of 36 possibilities, and so you end up with 0.472. And then at least 8, so that would be 8, 9, 10, 11, or 12. There are 15 ways you can get at least 8 out of 36 possibilities, so you end up with 0.417. So this 7.2 notes has been about sample space diagrams. We looked at specifically the Venn diagrams and then also the table sample space diagrams. So these are useful ways to organize your sample space in order to find your probabilities.